Greetings, peeps! We are back. Glad to be here. One of my favorite topics coming up, and perhaps yours too. It's called Newton's Universal Law of Gravitation, and where we need to begin is taking a look back at some of Newton's laws of motion, such as the third law in particular, okay? So look back at Newton's third law of motion, which is the one that regards action-reaction force pairs. So you might remember little tale about Len and I, and we were in this little battle, and it was not too devastating for me because I knew that physics was on my side, in that any wallop on his behalf would be walloped back in return by me. So his fist, for example, collided with my face, my jaw in particular, and made this wonderful sound when that happened. Vronk. I think that's the sound of the collision. That's not what I'm saying. That's actually the sound of the forces combining over here. And so the fist of Len combines and collides with the jaw of Morad, and two objects interact in this collision. We have an action-reaction force pair. Force of Len's fist is equal to negative force of Morad's jaw. They are equal and opposite. That's what Newton's third law says. It also says in this scenario that forces always come in pairs. So there's another situation I want to take a look at, and that is scenario 2. We have free fall. This is a medicine ball falling without the support of anything else. So it's just falling. You've dropped it from the roof or a desk or something like that, and it's falling, and there's no normal force. There's nothing else. Maybe there's a little bit of air resistance, but what we have here is the force of gravity, which is equal to mass times the acceleration due to gravity, g. Medicine ball, let's say it's 6 kilograms. But the problem is that in this scenario 2, we don't have an action-reaction pair. Is there only one force? Is this a violation of Newton's third law? So there's a big uh-oh, because that would be, well, it's a violation. It's not a good thing. So we have to rethink what's going on here if we just have this one force. And here's the question. If forces always come in pairs, hey, what gives? Where's the reaction force? So that's what we're going to kind of look at in this section. And fortunately, Isaac Newton developed something called the Universal Law of Gravitation that's going to help us answer this question. To begin with Newton's Universal Law of Gravitation, we've got to consider a famous story regarding Newton. And that would be the story that you may have already heard in your scholastic career, or maybe just heard of it in the general public. And so I apologize for those who don't care for the stories, but it's an important part of the background here. I know some of you just want to give me the equation, but nope, story time. I apologize. You know who you are. You know who you are. It's a story about the apple falling on Isaac Newton's head, and suddenly him claiming out gravity. This is gravity. So he discovers gravity because an apple falls on his head. Like, nobody knew that stuff fell before, and suddenly it's gravity. That's not quite the story. That's a myth. And so a more accurate version of the story deals with Newton perhaps leaning against an apple tree. Now, I don't have an apple. The best I can do is this onion, this white onion. So onions unfortunately don't grow on trees, but the idea is kind of the same. So maybe the onion falls while I'm hanging out under the tree. There's no onion tree, but it goes boom. Maybe it falls beside me. Maybe it fell onto my head. I don't know. And in Newton's day, it happened to be that the moon was out at the same time. So perhaps it was the evening. Okay, so he's looking out and he sees the moon and an object falling. And right then and there's an epiphany. He realizes something very, very important. And that is this. Now, Newton, of course, the inventor of Newton's laws of motion, right, Isaac Newton, recognizes from his own experience in developing these laws, like the first law of motion, that objects should continue in a straight line at constant velocity unless acted on by an external force. Okay, so he's looking at the moon, he's like, why is the moon continuing to wrap around the Earth? Why does it circle around the Earth? What's going on? What gives here? How come it's not just flying off on its own in a straight line away from the Earth. Something must be keeping it in that circular pattern, in orbit around the Earth. And when that apple falls, he recognizes that, wait a minute, the thing that fell onto the ground is the same force that's keeping the moon in orbit. It's keeping it trapped around the Earth. This force is what he ends up calling gravity. That's where the gravity comes from. People knew things fell, but where Isaac Newton was probably a true genius in many regards, but certainly in this one, it's making a connection that nobody had before. That connection was one that linked the Earth with the heavens. See, prior to Newton, the heavens were a separate place. It's kind of, a mystical place. Perhaps religions and theology thought it's the aftermath of what happens or where you go after you die if you've been good. But or it's just a place where the gods lived if you're part of Greek culture, okay? And that was in the stars and the clouds and all that. Well, now, mind you, there were no flying machines in Newton's day, so still the moon and the sun and the stars were regarded as a different place than on Earth. And what he realized is that the same stuff that happens on Earth, gravity that we see, things falling towards the center of the Earth, have everything to do with what's keeping the Earth in, the moon in orbit around the Earth. He linked the celestial with the terrestrial, space and all the objects there with Earth as we know the things around us. And that's a really profound thing, because that was not the thought pattern at the time. So that's where the true genius is. He really linked two things that we now know as pretty much the same place, our universe, our solar system, our galaxy, etc. But back then it was pretty revolutionary. So what he realized is that the moon would circle around the Earth, and there had to be some force bringing it in. And because it's circling around the Earth, what we have just learned about is this thing called centripetal force. There has to be a force that is going to point towards the center of the Earth. And this centripetal force he called gravity, all right? And he also noted that all the objects that fell on Earth were subject to the same force. This is the force of gravity. So that link gave him a clue as to how to explore this new phenomena that he coined gravity. Prior to him was another scientist, a very prominent one, by the name of Johannes Kepler. And in the early 1700s, he studied planetary motion. He took data from a scientist who didn't really understand the theory of the math, but he was good at collecting data, making observations with telescopes, the optical instruments of their day, and tracing the patterns of the planets. This man's name was Tycho Brahe. Pretty cool name. Tycho, not really a popular name with people today. Might be something you want to name your dog or cat or something like that. So Tycho Brahe was the guy who produced the data. Johannes Kepler was the guy that analyzed it. And what he did was developed what are known as Kepler's laws of planetary motion. So they're a little different from Newton's laws, which are about the real foundations of physics. These are more about empirical observations. So the data that was collected by Tycho Brahe, he combined with mathematics to describe the orbits of the known planets. Now, mind you, some of those telescopes weren't so powerful, so I think they probably went as far as Saturn, maybe Uranus, Neptune, I'm not sure, but they certainly hadn't seen Pluto, which has been since demoted anyway. That's a dwarf planet, by the way. But hey, that's okay. So there are 8 planets. Maybe they knew about 6 or 7 of them. And so what he did is just created a mathematics that accurately described where the planets would be, like the motion of the planets, that he would look and be able to predict exactly where they would be based on some of the data that he fit into mathematics. And mathematics is a powerful tool to be able to predict where things might go, okay? It had no foundation rooted in physics as to explain why the orbits are as they are. And so Newton comes along later, and this idea of gravity, the thing that's holding the moon in orbit around the Earth, might be useful in helping describe exactly why, mathematically, why this all happens from a foundational perspective of physics. So he would actually be able to describe the physics that actually works with keeping the planets in orbit around the sun, and then we'd be able to use that prediction and really, understand the foundations of the universe that much better. And so that's what Newton did. So next, that's exactly what we're going to discuss. What was Newton's findings that were so important? This thing called universal gravitation. Newton's universal law of gravitation. So this part 3 here is really about Newton hypothesizing the physical parameters that may describe this force of gravity that could be useful in working with the planets, but also perhaps every object out in the universe. And what he hypothesized and posed was that this invisible force, which is gravity between two objects, is proportional to two things. One thing is that it's proportional to the product of their masses. So let's say you have two objects and they're separated by some distance. The force of gravity between them is proportional to the product of their masses. So mass 1 times mass 2. Okay. And he also thought that the relationship was inversely proportional to the square of the distance between them. So the force of gravity is proportional to 1 over r squared. We're going to use r squared since your book does. We could use d squared. That's fine. And by the way, this fish thing that you probably know as alpha, which in some contexts refers to angular acceleration. In here, this case, when we see one variable alpha like m1 times m2, that alpha means proportional to. Okay, it doesn't mean equal. It means this. The force of gravity is proportional to m1 times m2, proportional to the product of their masses. So if I double mass 1, this whole thing doubles over here, and so the force of gravity between them doubles. If I double mass 1 and mass 2, that is going to be 4 times greater, 2 times 2, and so the force of gravity between them is 4 times as great. So it tells us something about the proportion, like how many times greater one thing happens when you change one of these variables. And what's in the denominator is an r squared. So we have a square in the denominator. We're going to do a whole lesson on something called the inverse square law that is going to govern how this works, because there's some little tricks that we can do to be able to understand this a little better. You can brute force calculate it, but whenever you have a square in the denominator, it's known as, well, an inverse square law. And that will be our study after looking at this equation. All right. Real quick though, if you were to double something in the denominator, double the distance between them, this radius, then the force would weaken by 2 squared or 4 times. If you would have the separation as 3 times greater, it would be 3 squared or 9. All right, well that's about as far as Newton got on this stuff. The ideas were revolutionary, but they still couldn't really use it in terms of the units available to them because they needed to know something called the gravitational constant. It's a number that goes in front of the equation that makes it work with everyday units so they can actually make the calculations and make the predictions that he was hoping to do and predict Johannes Kepler's, or predict the describe the reason why Johannes Kepler's planetary motion laws actually worked. So a century later, about 1798, there's another scientist by the name of Henry Cavendish. And he's really important for various reasons. Not only did he experimentally determine this value, this gravitational constant, using what's known as a torsion balance, he's the guy who actually discovered hydrogen. He isolated hydrogen and said, this is it, this is hydrogen. So he's a really prominent scientist in England in the late 1700s, early 1800s. And this is one of the things he did on behalf of physics. So it's a really important thing that we're going to look at because it enables us to make the calculation how much force is there between two objects that have mass. And that will be able to lead us to our original question, which is, where's that reaction force for an object that's falling towards Earth? And so here it is in its form. Newton's universal law of gravitation. Again, Henry Cavendish determined this. We'll look at his experiment as well and what transpired. How did it work? How did he get this number known as G? he determined it with something called the torsion balance. So we'll look at that experiment. And in the process, he's actually known for weighing the Earth. He's the guy who kind of indirectly determined the mass of the Earth by this experiment. Strange, but you actually can do that because of what Newton developed as the foundation for this type of physical phenomenon, gravitation. So here it is, what's known as Newton's Universal Law of Gravitation. Force of gravity is equal to big G. Now it's really important to write this as a capital G rather than a little g, because little g represents the acceleration due to gravity on Earth, as we know, 9.8 meters per second squared on the surface of the Earth. So big G is a totally different number and is the universal gravitational constant. So that's what it represents here. So this is the gravitational constant. And it's a weird number, but is the one that was developed by this experiment and other ones that followed. So you have G in front of M1, M2, and R squared. Now, after you have this number G, you are able to then calculate using units that we're familiar with. Like, for example, you would expect that the force would be represented in the unit of newtons, and it is with this G. And mass is represented by the unit of kilograms, measured in the unit of kilograms. And the unit of distance here, this radius, the distance between the two objects, is m squared, because it's a squared value over here. All right? And so with this study and the experiment, you determine that G has a specific value. And the reason why it's so important is because it's universal. This value works on Earth, it works in analyzing the planets, it works on galaxies on the level of anywhere in the universe, which is where this idea of, hey, universal comes from, that this idea of gravitation works everywhere, not just here on Earth. And it is 6.67 times 10 to the negative 11th, so it's a very tiny number. Newtons times meter squared over kilogram squared. Well, what happens when you use this constant here is that the kilogram squared cancels out, the meter squared cancels out, and we're left with newtons after using G. That's exactly what we want. This is the current accepted value. Now, other experiments have come along to maybe improve this number to a new decimal place, but this is the one that we'll use, 6.767 times 10 to the negative 11th. Oh, great. So how does this help us answer the question that we were looking for? Well, with this relationship here, we note, though, that gravity is a force of attraction. So it is only attractive. So it's an attractive force. It does not repel. It only brings things together. When we study electrostatics, which is, well, the fancy name for saying static electricity, where you have charges that are positive and negative, you can get repulsion and attraction depending on how you organize the combination of elements of subatomic particles. But in the case of mass, it's always attractive. So that's an important thing to know. All right, so we had our object, our medicine ball, of 6 kilograms, and it has an acceleration of 9.8 meters per second squared with respect to the Earth. Well, guess what that 6 kilograms is? It could be considered mass 1 in this equation over here. G would be a known value thanks to Henry Cavendish, and what we would need next is to figure out, okay, so where's it going? Where is that thing accelerating towards? And it's accelerating towards the center of the Earth, center of our planet. So what's down here as the other object, and not to scale, mind you, but this is our place, the Earth, right? And the Earth is attracting this object here, the medicine ball, and due to Newton's third law of motion, what has to be true is that forces come in pairs. And I know it sounds really absurd, but it's also true that this object is attracting the Earth towards it. Now, it has a different acceleration, but the force is the same. Opposite and equal forces, action-reaction. Okay, this force will be the same, this attractive force, for this object and for the entire Earth. So mass 2 is Earth in this case. And if we knew the mass of the Earth, which Henry Cavendish helped us find, we can look that up now. Well, not right now, but soon in another lesson. The idea, though, that's really important is that the force of gravity here is equal between these. We have our action-reaction pair. Even though it's an invisible force, the 6 kilogram object is attracting the Earth towards it, and the Earth, of course, is attracting the 6 kilogram object towards the center of the Earth. Okay, and this relationship here will tell us about the force. Now, anything on the object of the Earth accelerates at 9.8 meters per second squared. It's not mass dependent, and what we're going to see is why that's the case. It actually comes from here. And what we'll do is we'll look at that case in another lesson. We'll say, why is the acceleration constant for every object? And it comes directly from universal gravitation. The other deal is that, yeah, the Earth is accelerating towards this object, but because the Earth's mass is so huge, if we look at F equals ma, and this ma is huge, that acceleration of the Earth, I mean, the m is huge and the a is barely here at all, the acceleration of the Earth towards this object, the medicine ball, 6 kilograms, is going to be very, very slight, almost not measurable. And you add into the factor that we've got a bunch of other objects on the other side of the world and whatnot, and so the net result is that the Earth doesn't move very much, but it does move, just slightly. Other objects influence the Earth a lot more. We looked at the moon going around the Earth, and the moon, of course, if the Earth tugs on the moon and keep it in, due to the gravitation between them, actually keeping it in orbit, the moon tugs back on the Earth. And what does that do? Well, that creates tidal forces. That creates actually the tide system that we know. It jiggles the Earth and sloshes the water around and creates an odd shape for the Earth because of the fact that there's gravitation between the moon and the Earth as well. And so there are effects. The moon is a much bigger object, even though it's far away. It has a pretty strong effect on the Earth and produces things like tides. So this is really important for bigger objects. But as we'll look and see later, this idea of Newton's universal law of gravitation can extend to something as beautiful as satellites and coming up with geosynchronous orbit and putting a communication satellite up. How fast is it going to be whizzing by? What about the International Space Station when we see it above as this beautiful glittering light? So there's a lot of things we can do with it, and so that's what we're going to do during this unit. And I hope you're going to enjoy it. There's a lot of things we're going to talk about. We're also going to talk about how Newton, although this is very powerful, was corrected by another guy you probably heard of by the name of Einstein. So we're going to look at his physics and how it differs from this. Not as mathematical. We're just going to look at it from a conceptual level of, well, what's Einstein's view on this whole thing? How does it differ? And what is the current view of how the universe explains something like gravity? Or how we can explain something of gravity from the universe. That's what it is. This is a lot of talking in this unit, but it's a very rich one with lots of historical figures and whatnot. So I hope you enjoy it when we do it for reals. All right, I'm going to duck and give you a chance to take some notes down. This is what it is. Morad, out.